If you recall, our new project is some shortcuts to finding derivatives. There's kind of a lot of algebra involved when we're finding derivatives using the definition of the derivative, so we want some shortcuts to this process. Remember that what we're finding is the slope of a line tangent to a curve at a given point. The more general interpretation of this would be the instantaneous rate of change at a point. And we've talked about various notation. We've introduced various notations for this derivative function. One notation is to just put a prime after the name of the function and say f prime, and that indicates the derivative of the function with respect to whatever variable is in play. The Leibniz style notation is a variation on the slope as delta y over delta x. Slope is change in y divided by change in x. So we'll write normally a capital delta for change, delta y over delta x. But the instantaneous version of that for the derivative would be dy over dx. That's when our deltas are very small. And our delta y over delta x is 0 over 0. So when we make things very small, we go from the big capital delta to a lowercase d. So dy dx. Sometimes we'll say dy over dx. But once we all get the hang of it, and we are all hip to the lingo, we'll just say dy dx and know that it's dy over dx. So that's our shorthand way of saying it. We'll say the derivative of y with respect to x in general company. But when we're all around a bunch of experienced calculus students and we're all in the know, we'll just say dy dx. But we mean the derivative of y with respect to x. And this comes from slope is change in y divided by change in x. It's the instantaneous version of slope. It comes from delta y over delta x. It's that when the deltas are very small, we write dy dx. That's our limit. We can also use this d over dx notation. If we separate out the d over dx part, we can use it as a set of instructions. So if we just have d over dx, this is like using it as instructions. Say, find the derivative with respect to x of whatever comes next. That's what, it's like we take the y that was on top and we replace it with what y represents. Kind of like dx to the n over dx. Take the derivative of whatever comes next with respect to x. So that's what, when we write d over dx by itself. So you can imagine taking the y and separating it out. So we have d, I spelled x wrong. Our normal notation for this would be like dy over dx. And it's like we pull the y out front. Like pull that y out front. Take the derivative of all this stuff with respect to x. Note that I said take the derivative, which is another way of saying find the derivative. I don't know why take came along instead of just find, but that's just what we say. Language is annoying that way. This is going to be our favorite shortcut. If we can write powers of x, then we can try to write powers of x. So finding derivative starter set. If we can write just write terms with powers of x, then maybe we should write terms with powers of x. Let's demonstrate some stuff that you already know that you might not be aware that you already know. Sometimes in math, how you think something should work is just how it works. It does work that way. Let's find out. We're just going to go on instincts. So let's find the derivative with respect to x of, let's say, x to the fifth. Following our rule, what's the derivative of x to the fifth? 5x to the fourth. We have assimilated our rule. So 5x to the fourth. Any question? Multiply by the exponent, and then subtract 1 from the exponent. Multiply by the exponent 5, subtract 1 from the exponent, make the new exponent. So 5x to the fourth. Easy, right? Like I said, your favorite rule. Now I'm going to start changing things up a little bit. What if I want the derivative of 3x to the fifth? What is the derivative of 3x to the fifth, not having told you anything about how this works? Who's saying 15x to the fourth? Whose first thought was 15x to the fourth? I need to know who to flunk immediately. I'm just kidding. That's exactly what you would do. All I've done is multiply by the constant 3. So can I just multiply the derivative by the constant 3? And the answer is absolutely. How you think it should work is exactly how it works. So what we're saying is here, if we have the derivative of a constant times a function, it's just that constant times the derivative of the function. So what we're saying is that if we have the derivative of some constant times a function, we can ignore this constant. We just carry this constant along. I don't know what word you're going to use to think about this. But the derivative of a constant times a function is that constant times the derivative of the function. Sometimes people say, we just keep the constants, just carry the constants. Some people say, carry the constants. I don't know where that comes from. I picked that up from a student. I don't know where they got it from. Sometimes it's said we can ignore the constant. I'm not really a fan of ignore the constant because it has to stay there, but we're not like, it's not changing the operation in any way. But ultimately, all that matters is that you multiply the constant by the exponent for our first. All right, I'm gonna change these up a little bit more. Right now you're thinking, dude, you didn't change anything. I go, but wait, there's more. Actually, there's less because I'm going to do subtract minus, let's go with 7x squared. What is the derivative of 3x to the fifth minus 7x squared? What did I change? What am I doing to mess with you here? Put two terms, yes. Well, I can't, because one's an x to the fifth and the other one is x squared. They're not like terms. I can't subtract those things. This is as simple as it gets for that subtraction. What should we do? Yeah. 15x to the fourth minus 14x. How many of you would try this crazy idea? It's not a crazy idea. It's exactly what we would do. If we want to take the derivative of a bunch of terms, just take the derivative a term at a time. The derivative of a sum is a sum of the derivatives. The derivative of a sum is the sum of the derivatives. Nice planning on my part. Cram it all in there. The derivative of a sum is a sum of the derivatives. I need to highlight something. I'm gonna write the same thing, just with like some color coding. So don't be like erasing what you wrote down if you just copy that down. I'm also gonna scoot it over. So the thing that we've added is I've put terms inside my derivative. So the derivative of a sum is a sum of the derivatives. That means we take the derivative of f of x and then just add that to the derivative of g of x. We can say that the derivative of a sum is that sum of the derivatives. So secretly, your instincts told you that differentiation is a linear operator. You wouldn't have phrased it that way, because the time we start talking about linear transformations, you've already been through this class. But what this means is that differentiation is a linear transformation. Differentiation respects vector addition and scalar multiplication. So what we're saying here is that differentiation is a linear transformation. So for those of you who want this is the DVD bonus material. So if you want the fancy DVD bonus material, what we're saying with these two rules is that differentiation is a linear transformation. Because differentiation respects scalar multiplication and vector addition. That's just fancy words for this works like we expect it to work, because this is what you would have guessed. My favorite way to do this is, instead of talking, if there were fewer people, I would make a quiz and I would have these problems on the quiz. I would have told you that it's nx to the n minus 1 and then given you this as a quiz. You're like, well, how do we do this? I'm like, oh, I don't figure it out. And then you guess, and that was correct. That's a low risk, making you guess on something, because how you think it should work is how it works. That's just how you probably think it would work. Most people would go with these options. That's how it would work. And what that does is it positively reinforces guessing, which should be the goal of what we do in class. I want to create positive reinforcement of guessing. But that's hard to do. The difficulty I have thinking about teaching math from a behavior modification standpoint is that I don't really have a good positive reinforcement, right? I don't have a good reinforcement item or schedule. I don't have a reward. I did one time. I worked at a high school once. And when you work at a high school, you become a conduit to companies' access to young people with developing brains. And so when I was teaching high school, Snickers had come out with variant Snickers. And they had a Snickers that had, I don't know what the fuck was in it. It was like, I don't know what's in a normal Snickers anymore, because I'm too old to eat candy bars anymore, but they had like the variant Snickers. You know how Snickers have variants? Like there's one with peanut butter and there's one with all kinds of variants. Maybe there's like a gluten-free one. I don't know. Maybe there's one with pizza inside. That sounds disgusting, but I don't know what the kids are into these days. But anyway, the end result was Snickers is like, oh, let's send boxes of these fun-sized Snickers to high schools. They'll pass them out to the students. Then the students will take their parents' money and buy the full-size bars at the local convenience store. And they're like, oh, brilliant marketing. Get them when they're young. And what if we send them some cigarettes too? It's like, oh, no, they get mad at us when we do that. Oh well. So anyway, what happened was I get to work. I'm actually early for once. Weird. Walk into the faculty room, the faculty mail room, check my mailbox, look over here. There's like a 2-foot cube full of bite-sized Snickers. Fun-sized Snickers, they call them, right? And it's like 2 feet by 2 feet by 2 feet, just filled. The box went under a hopper that was full of bite-sized Snickers. And they just like all filled that shit up. I'm like, oh, what is this? I said to no one because there was no one in the room. Because like I said, I was early for once. I'm like, oh, what the F is this? And then I looked in the hall and no one was there. And I looked in the office and no one was there. It had apparently been delivered the day before. Someone opened it up, probably grabbed a handful. I'm probably supposed to grab a handful and give to my students. And so I grabbed the entire box and brought it to my classroom. Walking down the hall, colleagues walked by. What you got there? Box. What's in the box? Fuck off. Mine. So I go to the classroom, and at the time, I would have like the students do the homework. Then the next day we would go over the homework. It's like, all right, who's got problem number 1? And someone would volunteer problem number 1. And it was a usual class, right? No one wants to say anything. But today I had a secret weapon. I was standing at the lectern, little the half a podium that sits on top of a desk. And I had filled that bitch with a bunch of Snickers, bite-sized Snickers. I'm like, oh, who's got the answer to problem number 1? And like 10 minutes later, because they're high school students, they're trying to be cool. Never mind the fact that they're high school students. It is not possible for them to be cool. It's like physically impossible. They're 14-year-olds. 14-year-olds cannot be cool, but they're trying. So respect. So I'm like, oh, who's got the answer to problem number 1? And finally, my reliable student is like, oh, 7, whatever the fuck the answer was. I'm like, oh, correct. And I grabbed a Snickers and I tossed it to them, and then they caught it. And every single other person in the classroom was like, oh, it was like a room full of puppies instantly. They're like, oh, no. If they had ears, they would have been like, oh, whoa. What happened? And then problem number 2 came up, and the rule was you couldn't just answer all the questions. I don't care if you had all the questions. I'm like, oh, that's great. Who's got problem number 2? Someone raise their hand. Well, yeah. 5. I'm like, oh, yes. Threw them a cookie. It still works. That week was the most response I had, and it carried over to following weeks. I even straight up told them the next week, so I'm out of Snickers, guys. But it still carried on. The behavior still carried on. They couldn't stop themselves because I had modified their behavior. I only figured out what I had done later on because I started training dogs. I'm like, oh, now I see why the Snickers was so effective. Because now I have a dog, and I can get the dog to do things, and I don't have to pay him every single time. What are we talking about? I don't have candy to hand out. So I don't have like cookies to reward the behavior. If I had really been thinking about it, I'd be like, all right, what's the derivative of 3x to the 5th? And the first person that's like, oh, 15x to the 4th, if I had a clicker, I'd be like, I'll click, then treat, then yes. What? All right, so let's talk about, differentiation is a linear transformation. That's the fancy thing for what's going on here. Differentiation respects scalar multiplication, and differentiation respects vector addition. I know they're functions, but functions are vectors in this line of thinking. Let's think more about some derivatives that we will know. Remember that the derivative is the rate of change. The derivative is a rate of change. Recall from the previous page, derivative is rate of change. And we also have that rate of change is just slope. Slope of tangent line, but slope. So I want to think of rate of change as slope, but the derivative is the rate of change, the derivative is the slope. So tell me about the rate of change of a linear function. What is it about the rate of change that makes a linear function linear? A linear function has a constant rate of change. A linear function has a constant slope. The slope is the same everywhere. The slope of the tangent is the same everywhere. Let's look at a linear function and see that happen in the derivative. If y is equal to 1 plus 2/3 x, what is dy dx? Actually, let's drop the 1, because that's going to be actually the subpoint. Let's make a 0. I'm going to take this whole function just down 1 unit. Why do I make things so complicated? Let's suppose y is just 2/3 x. Here's a linear function. What is the slope of this line? Let's start with an easier question. What is the slope of this line? The slope is 2/3. What is the derivative of 2/3 x to the, what power is here? To the 1. What is the derivative of 2/3 x to the 1 power? That is, what is dy over dx? 2/3 x to the 0 and x to the 0 is just 1. So the slope is the derivative. The derivative is constant. It makes sense that the derivative is constant because this was a linear function, and linear functions have a constant rate of change. Two-thirds x, a linear function, is its own tangent line. Let's think about a simpler linear function. Why don't I just use one from the map? Think about the equation y equals 5. What does this graph look like? What's the graph of y equals 5 look like? This. For those of you at home, we're going like this with our hands. So we're saying horizontal line. International symbol for horizontal line. It's just a flat line. What is the slope of a horizontal line? 0. So this is just us knowing stuff about horizontal lines. Slope of a horizontal line is 0. So is there an x here? If I was going to force an x to be there, what's the exponent on it? 0. And so what is the derivative of 5x to the 0 power? 5 times 0x to the who cares? 5 times 0 is 0. The derivative of a constant function is 0. This makes sense. Of course it is, because a constant function is a horizontal line, and the slope of a horizontal line is 0. The derivative of a constant function is 0. Because of course it is, the slope of a horizontal line is 0. I guess this goes both ways. So if we want to do an infinite number of examples at once, what is the derivative of b plus mx? We can go a term at a time. The derivative of b is just a constant, so the derivative of b is 0. The derivative of m times x is mx to the 1 minus 1, mx to the 0, or just m. So the derivative is m. This makes sense. B plus mx is a line with slope m. The derivative of a linear function will be the slope of the function. Derivative is slope. Rate of change is slope. Derivative is rate of change. Any questions? How's everybody okay? What kind of rate of change? Oh, sorry, not derivative. I wanted to reverse this, go back to rate of change. So let me take out derivative and write rate of change. What's the rate of change of a quadratic function? Remember, we classified three important kinds of functions by their rates of change. Linear functions had a constant rate of change. Exponential functions had a proportional rate of change. What kind of rate of change did quadratic functions have? Let's find out. We have mechanics now. We're trying to make this match up with the mechanics. You know I'm going to write down a generic quadratic and say what's the derivative. So let's think about it from a mechanics standpoint. Let's suppose that y is equal to ax squared plus bx plus c. X is the variable, a, b, and c are constants. What's the derivative of ax squared plus bx plus c? 2ax plus bx to the 0, or just b, and the derivative of c is 0. Oops, this is not equal. So when we took the derivative of this quadratic function, we ended up with a linear function. So here we have a quadratic. And the derivative of that quadratic is linear. And previously we had pointed out that the rate of change of a quadratic function is linear. The derivative of a quadratic function is linear. Of course it is. Look what we do in the derivative process. We multiply by the exponents, then we subtract 1 from the exponents. Quadratic minus 1 is linear. Quadratic is degree 2. Subtract 1 is degree 1. We go from quadratic to linear. The rate of change of a quadratic function is linear, so the derivative of a quadratic function is a linear function. Any questions? How's everybody okay? It's just too easy? Is it too difficult? No one ever wants to say it's too easy, right? My thought, if purpose, I go, this is too easy. I go, great, I'll increase the difficulty. And I go, no. I want the easy mode. I'm setting the difficulty to easy. Any questions? That's what I have to do on video games where reaction time is any kind of factor at all. I just can't play on the higher difficulty level. I'm just way too slow. You know what I mean? So if you want to make fun of me, I bet Leach plays this game on easy mode. Yeah, totally. Like if there was like a first person shooter, like a competitive one, if you watched it from my end, it's like, oh man, is that guy spawn camping you? It's like, well, no, I'm just really bad at this. Because it'd be like, oh, look, an enemy, and then the screen is red. And then I have to respawn. It's like, oh, look, an enemy. I'm gonna, screen is red, gotta respawn. Look at, that. Yeah. Oh. All right. The other one that we have running around is that the rate of change of an exponential function is proportional. That one's more complicated. We'll have to think about that one. So that will come up later. Right now, what we're dealing with, what we have is the derivative of x to the n is nx to the n minus 1. If we can write things as powers of x, then maybe we should try writing things as powers of x. We're trying to make the association that derivative, up here, derivative is rate of change, derivative is slope, because rate of change is slope. The whole point of this exercise is that we care about the slope of the line tangent to a curve at a point, because it tells us how the function is changing at that point. It is a speedometer on the function. Your speedometer is an instantaneous rate of change machine. If you drive from point A to point B, and if you drive 300 miles in 5 hours, you have an average speed of 60 miles per hour. But a lot of times you were going faster than that, and a lot of times you were going slower than that. Your average rate of change was 60 miles per hour. At some points in that journey, your speedometer said 0 miles per hour because you were stopped. Your instantaneous rate of change was 0. At some points, your instantaneous rate of change was 65 miles per hour, because I know everybody is going to behave and follow the speed limit. Maybe 70 or 75. Should be 80. So your speedometer is saying what's happening now. At some point on the drive home, my speedometer is going to say 60 miles per hour. Oh, wait, no, I'm going to be on Skyline. So it's going to say 50. It'll say 50 miles per hour. And I assure you, police officers, that will be the highest number it will find. But that doesn't mean my average speed the whole time was 50 miles per hour. It's still going to take me like 15 minutes to go the 5 miles it is home. But my instantaneous rate of change, the derivative of my position with respect to time, will be 50 at some point. All right, that's going to do it for today. Tomorrow we'll do some more mechanics about this derivative. Focus on this linear transformation business. That's it for today. Everybody have a good day. I'll see you tomorrow. And thanks for playing.